Hello, this is Petro and you are watching WellCode, and in this video we're gonna talk about Facebook Hacker Cup and also about the online coding contests. As you may know, Facebook Hacker Cup is happening right now. It's a contest which takes part every year. It has 4 programming challenges and it has more phases. If you do really well in the first phase, in the qualification phase, you will advance into the next one, and this goes on until the finals, which are for about, I think, 20 participants. And I believe that coding contests in general are really good training for yourself. You'll be able to do better at the interviews, because the problems for coding contests are a bit harder than the ones you receive at the interviews. Another big advantage for programming contests is that you can put them in your CV. So if you participate in Facebook Hacker Cup and you qualify for round 1, you can put that in your CV, and recruiters may look at that. Just as a disclaimer, I'm not a recruiter. I don't represent the opinion of any company. It's just my interpretation of how everything works. So when I first applied for internships, I didn't have a lot of cool things in my CV. I didn't have any work experience. I didn't have a lot of personal projects. And the only thing I was good at were programming contests. And in the first year, I got a lot of interviews. I interviewed with Google. I interviewed with Facebook. And I believe that having good results in coding contests not only helps you for training, but also helps you develop a better CV. There are 2 popular programming contests. There's Facebook Hacker Cup, there's also Google Code Jam, and they are some other important contests. If you're in college, you can participate at the ICPC. Usually you want to participate in the most popular ones for the CV part, because if you participate in ICPC, recruiters may know how to compare you with other people. So if you qualify for the world finals, that means you're among the best programmers in the world. Even if you participate in a very difficult contest, if it's not that well known, you'll have to explain a lot in the CV, or maybe you'll have to explain that to the people from the company you're interviewing with. I'm not saying you shouldn't participate at the other contests. I'm saying just that the big ones get you a better image in your CV, but those are just once per year, and obviously taking part in 3 or 4 rounds of programming contests is not enough in order for you to be well prepared for a contest. Okay, enough with all those talking, and let's get into more practical things. In order to take part in Facebook Hacker Cup, you just go on Facebook, you search for Facebook Hacker Cup, and then I think you have to click on the sign up button and you will register for the competition. I already have all my data filled in. Obviously you won't see it because I don't want to share my address with you. And another interesting thing is that on the registration page you can opt in for being contacted by Facebook recruiters in order to get job offers. So if you're doing really well, you may also get a job at Facebook. Okay, and now this is the link for the qualification round, and I'm gonna click it, and these are the 3 problems. I have 50 more hours to solve them. You have to read carefully through the instructions. The different thing compared to maybe other platforms you've been used to is that for Facebook Hacker Cup you have to download all the input files on your computer, run your code. You can code in any language that you want, and then provide the output for the input that's been given to you. So this is a big difference compared to other platforms where you just upload your code and the server tests it. Here you have to upload the output for the input that's been given to you. You also have to provide the source code in order for them to make sure that you're not cheating, and this is the difference. So this may be an advantage for people who have really fast computers. They may be able to implement some not so efficient algorithms for solving the problems. Obviously, if you have a high complexity solution compared to the optimal one, and it does a lot of computations, even if you have a really fast computer, it won't be enough. So it's better just to solve the problems well and think about the best solution you can come with, or a good enough solution which, when you replace the variables in the complexity formula, you obtain a decent amount of computations. Usually it's about 10 to 100 million computation. That's good, and it also depends on what kind of operations you're doing, but usually 10 or 100 million it's fast enough for this kind of contest. Okay, so let's get going and read the first problem. I'm gonna talk loudly, so you're gonna understand what's going on into my mind. That this is a really good idea if you are applying for interviews, because when you are at an interview, it's best to tell the people what you're thinking about, so that they can see that your mind is really working. And so it's bad just to not say anything and just write all the code, and after 10 minutes, oh, I'm done. So be aware of that. If you're applying for interviews, it's good to practice, so while you're solving problems you can talk loudly to yourself, and you'll see how I do it. Usually I'm really good at talking and explaining, because I've been teaching computer programming for 7 years. But let's end the talk and start with the first problem, called tourist. The Facebook campus has n different attractions numbered from 1 to n in decreasing order of popularity. The name of the 8th attraction is AI, a unique non-empty string consisting of at most 20 characters. Each character is either a lowercase or uppercase letter or a digit. Alex enjoys visiting the campus repeatedly for tours, including the free food. Each time he visits, he has time to see exactly k of the attractions. To decide which k he'll see, he sorts an attraction in non-decreasing order of how many times he's already seen them before, breaking ties in decreasing order of popularity, and then chooses the first k attraction in the sorted list. In other words, he prioritizes seeing attractions which he's seen the fewest number of times previously, but also opts to see the most popular attraction out of the ones he's seen an equal number of times. Alex has visited the Facebook campus v-1 separate times already, and he's about to go for his 5th visit. Given that he's always followed the rules stated above, and that he'll continue to, he'd like to determine which k attractions he'll see on his 5th visit. He'd like to list them in decreasing order of popularity. In other words, in the same relative order as they appear in the given list of n attractions. Okay, so this is the first problem. As usual for this kind of contest, you have all the test cases in one file. So you have to read first the number of test cases, which is t, and then you read the input for each problem. It looks like a easy problem. You just have to simulate, or not, because v is 10 to the power of 12. Okay, so if v was smaller than 10 to the power of 12, it would have been very easy. So we would just simulate the whole thing. We will search through the list and see which are the attractions which were visited the smallest number of times, and do that v times. But because v is that big, we obviously can't do that. And the good thing when you don't have an idea about how to solve a problem is just to check the examples and try to understand why the output is what it is. So let's see. You have you visit just one attraction, and then you have what's this free? I forgot what it is. Oh, and we carry the 3rd visit. So those are in the decreasing number of popularity, I think. Yeah, it's in decreasing order of popularity. So the most popular one is the like sign, which will be visited at the first time. Then it's arcade, which is second time, and the 3rd time it's sweet shop. So basically for k equals 1, you just cycle through the list, and then you go back at the beginning and cycle through the list. And let's see, here you have this is this is a really big test case, so you have to simulate that 100 times. So I'll skip that. Another good idea when you don't know how to solve a problem is just to check for smaller cases. Even if you don't have an example, you can think about, oh, what happens when k equals 1? What happens if v has a small value? Let's say it's 2. So let's see what's this third example like. No, this is actually the fourth example. I think this is the best one. So during the first visit, he sees like sign, arcade, and sweet shop. Then for the second visit, it's swag store, like sign, and arcade. And for the third visit, it's sweet shop, swag store, and like sign. But you'll have first like sign, then sweet shop, and then swag store. This is like sign, sweet shop, and swag store, and this is the output. Yeah, so and now we have an idea about how the process works, and my intuition tells me that because v is so big, we don't have any other choice than finding a formula. And every time and we see that every time there's a continuous sequence of attractions which he'll visit, so we just care about what's the offset of the first item in the list. And for finding the offset, we may think of the list as being infinite. So we can think that we have one, and let's just not for an easier explanation, I'll just number everything from 1 through infinite. So first attraction is called 1, then it's 2 and 3, 4, 5, 6, 7, 8, 9, 10, and so on. And each time you visit k attractions. So the first time you visit from 1 till k, second time you visit from k plus 1 till 2k, and so on. So we can see a really straightforward formula. So each time you visit from I times k, I times I minus 1 times k, plus 1 times k plus 1, until I times k. This would happen if the list were infinite, but here it's not infinite, so we need to think about reducing everything to the first n elements. And this is a classical division problem. We'll use the remainder of division. In order to use the remainder of the division, which takes values from 0 till the divisor minus 1, we want to number everything up from 0. So instead of being from 1 to k, we'll use from 0 to k minus 1, then k times 2k minus 1, and the formula will be I minus 1 times k till I times k minus 1. And obviously this will be modulo n, so everything will be for v we'll have v minus 1 times k till modulo n till v times k modulo n. And we have to be careful about this thing because we are working modulo n, so this thing may actually be larger than this one, and we don't want to make a mistake here, so we'll have to have two cases. If this one is bigger than this one, we'll iterate from this one till the end, and then we'll start from the beginning until we reach this point. Okay, so let's go to the implementation. You'll be able to see how I'm writing code for this problem. First of all, I need to create the source file. I'll call it problem1 problem1.cpp because I'm working in C++ for this problem. So just to be sure that you understood what I was trying to do, I'll explain it again. So if we have 6 attractions and we visit 4 each time, we can imagine first of all, in order to understand the solution in a proper way, that we have an infinite list. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. First time we visit the first, I said that we will visit the 4. So we'll visit 1, 2, 3, 4. Then we'll visit 5, 6, 7, 8. But 7 corresponds to the first element. 8 corresponds to the second element, actually. And in order for doing this in a pleasant way, without inventing formulas which are too complicated, we can renumber everything from 0. So instead of having this, we'll have 0, 1, 2, 3, 4 until 5, and here we'll have 0, and doesn't matter. And if you look carefully, 6 will be if we work modulo 6, because we have 6 numbers, 6 will be 0 modulo 6, 7 will be 1 modulo 6, 8 will be 2 modulo 6, and this thing goes on and on. Okay, so let's start writing the code. I always include IOString because sometimes I'm making mistakes and I use print statements in order to find out the mistakes, even though the best way for you to find mistakes is just read the code and try to understand it without using any external help. This thing helps you a lot when you're doing interviews, because at the interviews you don't have an IDE, you are not able to run your code, you just have to write everything from your head, and you need to be really careful not to make mistakes. Then I'll use fstream for reading and writing input, and string for the how do you call it, for the attraction names. std. And for each test case, this is do I also need to print case 1, case 2? Yeah, okay. So if I'm printing in this way, I'll need to have problem. I just name it p1.in and p1.out. And now I'm reading the number of tests, and then I'm doing a for loop. T goes from 1, t is smaller than big T, plus plus T. And now I have to remember all the input, which is there are only 50 strings. And how long is the longest one? At most 20 characters, so it's 50 times 20, which is 1000, I think. Yeah, it's 1000. Okay, so let's string attractions which has 50 elements, and now let's read its n, then k, then what was the last thing? Yeah, it's v. But for v, we need to make it of type long, because otherwise 10 to the power of 12 won't fit. So let's read the input, n, k, and v, and let's read all the smaller than n. Let's read all the attractions. So f is attractions of I. Okay, so let's read all the attractions, and now we just have to apply the formula. So start is v minus 1. we don't have to care about everything being long because v is already long. So this is times v minus 1 times k, and obviously everything modulo n, and n will be v times k modulo n. And yeah, obviously I used uppercase letters because it makes the code cleaner if you use uppercase letters for input. Yeah, usually when you are designing your own solution, you need to have better names. So in order to have better names, I can use here start position and end position. I don't think they are that strict for interviews. Obviously, they won't like it if you just name those two variables S and E, but it's a good idea to have a balance, like have decent naming. Okay, and now we just have to print case D, and then yeah, and now we have two cases. This is start pos is smaller or equal than end pos. Then I just have to iterate from I equals start pos I is smaller or equal than end pos plus I, and now I'm just writing them in order of popularity, so they are already ordered by that, so I just need to write attractions on the position I and then leave a space, and else we need to iterate first of all from the beginning because those are the most popular ones. So I'll iterate from I equals 0, I is smaller or equal than end pos plus I. So I'll just copy this thing, and then for t equals end pos E is smaller than n plus I print this thing again, and afterwards we'll just leave a new line for the next test case. Okay, hopefully the code is good. If it's not good, you'll see how I'm debugging the code, how I'm trying to find my own mistakes. And I'll create the file, which is called p1.in, and I'll copy the input, and let's see how it works. I have to execute it, and let's see how the output looks like. So the first one is actually the first one prints everything, which is wrong. This is also wrong, and everything is wrong. Okay, let's try and find my mistake. So I'm reading N, K, and V. First of all, I'm checking that I'm reading the whole thing in the correct order. So I'm reading N, K, and V. I'm reading everything from position 0 because we're working modulo. And we're computing the start position, which is V minus 1 times K. It's not K minus 1 times K because we're doing, we're starting where the last thing stopped, and it stopped at V minus 1 times K minus 1. So the next one will be obviously V minus 1 times K until V times K, this thing is everything minus 1, because it's the position before. As I've written here, I'm not good at, no, actually I was right. Or wait, no, this minus 1. I've made a small mistake here. So here is minus 1. Because otherwise we would have K plus 1 elements instead of K. And yeah, I've did the formulas wrong. Let's check if now it's right. So first one is sweet shop, then it's Folks, Gazebo, MPK20 Roof, Wooden Sculpture, and Birani. Then it's like sign, arcade, sweet shop, like sign, sweet, like sign appears 2 times. Hmm. For case number 4, what was case number 4? 1, 2, 3, 4. So the first one was those 3. Then it was this one, and this one. And the last one was Sweet Stop, Swag Store, and like sign. So like sign appears 2 times. What's the reason for it? So it will be v minus 1, which is 2. 2 times 3 is 6. Modulo 4, it's 2. So it begins at sweet shop. And then v times k, it's 9 minus 1 is 8. 8 modulo 4 is 0. So the first thing starts at 0 and goes to the end pose. But here, this one is not from end pose, it's from start pose, because start pose is larger than end pose. And I've again did a silly mistake. So there are 2 cases. Let's draw them. So you either have a start position and an end position, and you just iterate from start to end, or you have the other way around. So you have start position and end position, and you need to iterate from here till here. And this is the second case, and this is what I was doing wrong. Let's execute the code again and check out like sign, sweet shop, sweet, swag store, like sign, arcade, swag store, and wall of phones. Okay, so this is it. I'll download the input and submit it. Give me the input. I have 5 minutes and 30 seconds to submit this. This needs to be p1.in, and let's see how this thing looks like. It's too big, but hopefully it will work. Let's see if things look decent. There are 80 test cases. I have 80 here. All right, let's submit the code. So I choose the output. Cancel projects, Hacker Cup, qualification. And I think first thing was output. So I'm putting my output and also putting my source code. And I've submitted it. So I won't be able to see my score until the end of the competition. And now let's go to the next problem. First problem was really easy. I haven't read the problems before because I want to show you how I actually solve problems. I don't want to cut the video and show you that I'm the best programmer in the world, because I'm not. And even if I was the best programmer in the world, I think the best thing to learn from someone else is how to think about the problems and how one can overcome not having an idea, or how one can find his bugs quickly. Okay, let's read the second problem. This should be more difficult. Consider an n-degree polynomial expressed as follows. It has n plus 1 terms. You'd like to find all the polynomials x-intercepts. I don't know what's that. In other words, all the distinct real values of x for which the expression evaluates to 0. This sounds like hard math. Unfortunately, the order of operation has been reversed. Addition now has the highest precedence, followed by multiplication, followed by exponentiation. In other words, an expression like a to b plus c times d should be evaluated as a to the power of b plus c times d. For our purposes, exponentiation is right associative. In other words, a to the power of b to the power of c is a, everything to the power of b to c, and 0 to 0 is 1. The unary negation operator still has the highest precedence, so the expression minus 2 to the power of minus 3 times minus 1 plus minus 2 evaluates to minus 2 to the power of, yeah, everything. Yeah, so it's the way I'm, that is still the regular minus. Input begins with an integer t, the number of polynomials. For each polynomial, there's a line containing the integer n, the degree of the polynomial, then n plus 1 lines follow. The ith of these lines contains the integer p minus 1. This sounds like a challenging math problem at the first read, but we don't need to feel discouraged or depressed or quit the contest. We need to somehow find the solution, because usually if you're not at the really advanced competition, like at the last or the phase before the last part of Hacker Cup, the problems have easy solutions. And this is one thing that one of my teachers told me when I was in high school. There is no such thing as hard problems. There are just problems which we don't know how to approach. So let's see what the approach for this can be. As I said before, let's look at the examples and try to make sense of what is in this problem. So let's take the first example. So this is the degree 1 polynomial, which has two terms. So this will look like, will look the following. So I'm having 1 times x to the power of 1. Don't forget to write that, because here the exponentiation is not the regular kind of exponentiation, plus 1 times x to the power 0. And now let's make sense of what's happening here. So addition now has the highest precedence. So for this thing should be evaluated as following. So this needs to be evaluated as following. Actually, I'm not able to make sense of it, but hopefully I'll figure out a way. Let's see. All right. So it's a to the power of b plus c times d. This will be evaluated as a to the power of b plus I'm still not able to understand this. So addition has the highest precedence, followed by multiplication. Then we need to do, oh yeah, this is obvious. So if we have this thing, it will be b plus c. I think it's easier if we rewrite the thing they just put there, plus c times d. So if addition has the highest precedence, then we'll just put here some brackets. And after we put all the brackets for addition, then we'll put all the brackets for multiplication. And then after we put all the brackets for multiplications, we'll do the raising to the power. So if we have the general form, I think it's easier actually for this thing to just look at the general form. If we have Pn times x to the power of n plus Pn minus 1 times x to the power of n minus 1, x to the power of n minus 1, plus so on, plus P1 times x to the power of 1 plus P0. Then we just have to put brackets to all addition signs. So here it's n plus Pn minus 1, and then it goes n minus 1 plus, here will be Pn minus 2, and so on. And here is 1 plus P0, and so on. And afterwards, we just put the brackets for multiplication. So actually, those terms, we know the values for those terms. So we'll have something like, for the first step, these are all knowns. So we'll have something like Pn times x to the power of, let's say this is An, and then we'll have times x to the power of An minus 1, and then we'll have times x to the power and An minus 2, and at the end we'll have just this thing will get inside there, so it will be just x to the power A0, which is 1 plus P0. Am I right, or have I made a mistake? P1x plus P, oh wait, here is P0 times x to the power 0. So this thing will be x to the power of A0. I have to be really careful for the last term. So then this means we're having P1 will go with the last term, so this will be plus P0. This will be actually A. Yeah, so we don't have any addition, so I think this one will be the last one. So it's x to the power of A0, which is this one, and everything will be times x to 0. And now we'll put the parentheses around multiplications. So it will be x times Pn, and then An. Oh, wait, this is not Pn. Oh, it is. It's Pn times x to the power of An times x, and then An minus 1 times x, and so on. So actually, after I tried finding a simplified formula, more simplified one than the one I first found, I tried replacing the first example in it and just found out an awesome thing, and I'll show you. So let's take the example. It's 1 times x to the power of 1 plus 1 times x to the power 0. And if we apply the rules, we need to do the additions first. And this thing will yield to 1 times x to the power of 2 times x to the power of 0. And now we want to do the multiplications, and then we'll do the raising to the power. And how raising to the power works is that you do the inner thing first. So this thing actually will be computed before this one. So then this means this is already 1. So we are having 1 times x to the power of 1, which results that 1 times x has to be equal to 0. And I made a mistake. Let's see what I did wrong. And I also looking at this 0.0 and I don't know what this is. So I forgot to read the output. For the ith polynomial, print a line containing for the ith polynomial, print a line containing case I k, where k is the number of distinct real values of x for which the polynomial evaluates to 0. Oh, okay, so 1 is not a value. Okay, and here it's only when x equals 0, and in the second case there are no values, no other values. But I don't know what's with this 0.0. I think it's a mistake. Let's try and refresh the page. Then print k line. Oh no, then it says print k lines, each containing such a value of x in increasing order. But basically what we need to do, we need to have a 0 value here in the first term. So basically Pn times x has to be 0. And after that we just need to check if the whole expression evaluates to 0. So I assume that there are either the solution can be 1 or the solution can be 0, because basically you evaluate this from the right hand side to the left hand side, and what you need to have is to have a non-zero exponent. So basically here you have to have a non-zero, and then you have to have 0 here. So in order to have 0 here, you just say that x equals 0. But if x equals 0, looking from those terms, you'll just end up with this will be 0, this will be 0 until the end. So 0 to the power of 0 is 1. Oh wait, this is the order. Yeah. So here we'll have 0 to the power of 0, which is 1, and here we'll have 0 to the power of 1, which is 0. And then yeah, so basically each time you do this thing, you'll either have 1 or 0. And for knowing what's the number of solutions, if you have 0 or 1 solution, you need to look if you have an odd degree polynomial or an even degree one. So here is the first one, and here's the second one. First one is odd, second one is even, and if we're having an even number, then we have no solutions. But let's check our hypothesis again in order to make sure we're not doing any mistakes. I've read everything again, and I believe the trick to this problem is to write the exponentiation as an operator, because if you do this on paper, it will be much harder to see the rule. And I'll do everything again in order to double check that the problem is that easy and that I'm not making any mistakes. So let's write the polynomial again. So it's Pn times x to the power of n plus Pn minus 1 times x to the power of n minus 1. Each time there's a minus, I'll just assume that you'll do it right away. Then plus Pn minus 2 times x to the power of n minus 2 plus so on, P1 times x to the power of 1 plus P0 times x to the power of 0. Okay, let's put the parentheses. So it's n plus pn minus 1 times n minus 1 plus pn minus 2 times x to the power of n minus 2 plus so on. So here will be this will be the parenthesis, and here will be 1 plus p0 times x to the power of 0. Okay, so now we did the notation where an equals n plus pn minus 1. No, an is n plus pn minus 1. So if we rewrite this again, we'll have pn times x to the power of an times x to the power of an minus 1 times so on times x to the power of a1 times x to the power 0. Okay, now we put the parentheses again for the multiplications, and let's see what happens. So basically, now we assume that these values are calculated, and for evaluating the raising to the power, the exponentiation, sorry, I'm just translating from Romanian. Yeah, so if we're looking at the exponentiation, we'll evaluate everything from right to the left. So that means that this thing Pn times x will be evaluated the last time, and the only exponentiation I can think of which uses integers and yields to the result 0 is when you have 0 to a non-zero. Non-zero. So that this means that x has to be 0. And this means that each of those terms will be 0. So we'll have something like 0 to 0 to 0 to 0 to 0 and so on. But 0 to 0 is 1, and 0 to 1 is 0. So as we're adding zeros to the end, the thing will be either 1 or 0. And if we look at the first example, we'll just see that whenever we're having an even number, a polynomial of an even degree will have the result 0, and if we have an odd degree, we'll have a result 1. Let's check it again the last time, I promise. So it's 1 times x to the power of 1 plus 1 times x to the power of 0. And after we're doing this, we'll end up with 1 times x to the power of 2 times x to the power of 0. And this will be staked together. So we basically end up with 3 terms here. So this is it. And let's see what happens if we add another term. So let's say here would have been 1 times x to the power of 2 plus this thing. How many terms will this add? We do first the addition, so we have 1 times x to the power of 3 times x to the power of 2 times x to the power of 0, and then we'll have just one more term. So yeah, our assumption. So yeah, my assumption that each initial term of the polynomial adds one term in the final expression is true, and I'll just save this problem2.cpp, and I won't purchase Sublime Text now. I'll just copy this because I don't want to write case again. And I'll just have to read N, then the P's, which I don't care about the P's actually. So it's N. So I just read N and P. N and P. And this is the output. F, N and P. And now we'll just read for I equals 0, I is smaller than n because we're reading n plus 1 terms, plus I, F reads P, and yeah, and that's it. And now we're having two cases. If n mod 2, so if n is odd, this means n mod 2 is not 0. So if you just write an expression inside an if, it will be true if you're if it's non-zero. So if the expression is non-zero, yeah. So if this is true, then I'll output just one new line 0.0 new line, and otherwise I'll output just G is 0 new line. And I'll do the .txt because that's how, oh, this is wrong file, to p2.txt, and the output will go into out. So let's see if this thing works. Oh wait, I've written to the wrong file. Now I've written to the right file, and let's check p2.out, which is empty. Why is it empty? p2.in, yeah, because I'm reading from p2.in. It's txt. All right. So case 1 is 1, it's 0, 0, and case 2 is also that, but I think I have trouble reading the input. So let's print and let's see what I'm reading from the file. I'm reading 1 and 9, but I should have read 1 and 4. Yeah, so I'm reading N. Oh, I shouldn't have read here P, because P gets, I read an additional P. That was the mistake here. So right now it's case 1 is 1 and then is 0, and I'm pretty confident that the solution is right, even though if you see a mistake, let me know in the comments. Probably when we release this video, the results will already be published. Yeah, I wonder what was the mistake and how could I have caught it. Yeah, let's get the input, and this should be p2.txt. All right, p2.txt. There are a lot of numbers, a lot of them don't matter, or I think they don't matter. And the output is 0, 0, 0, 1. Yeah. Okay, let's submit the problem. p2.out, and source code is problem2.cpp. Let's check again that this is the right thing. Okay, submitting. Solution successfully submitted. Now I should be higher up in the scoreboard. All right, this is me. And okay, let's jump to the next problem. A fun thing happened after I was about to open the third problem. I just saw that I might have a wrong solution because if b was 0, then the first term could be 0, and I didn't pay enough attention to that. But then I read through the statement more carefully, and I saw here that pn can't be 0, and I was, oh yeah, this is good. I haven't made a mistake, even though it may have caught me and I would get 0 points. So let's get to the hardest problem and see what's it about. Ethan's doing his very first programming assignment implementing a contains function. This function takes two strings a and b and returns true if a is a substring of b and false otherwise. Here's the algorithm that Ethan has come up with. Note that bar denotes the length of a, and the individual characters of the strings are one indexed. Set I and j to be equal to 1 if I is larger than the length of a, return true. If j is bigger than the length of b, return false. If ai equals bj, increment I and j by 1 each and return to step 2. If I equals 1, increment j by 1 and return to step 2. Set I to be equal to 1 and return to step 2. As the TA in charge of grading Ethan's assignment, this doesn't look quite right to you. To make sure Ethan doesn't get any more credit than he deserves, you'd like to find some inputs for which his algorithm returns false even though it should return true. The professor teaching this class has provided you with a half-written list of test cases. In particular, it's a list of inputs for the a parameter, and you're free to come up with your own inputs for b parameter. For each given string a, you want to find the string b that will cause Ethan's algorithm to return the wrong output false instead of true if possible. A will only contain uppercase alphabetic characters, and B must follow the same constraint. The test cases shouldn't be too large, so B must also contain at most 10,000 characters. Okay, so we need to check if A is a substring of B, and we need to understand what this algorithm is actually doing. And for doing that, it's maybe a good idea to just take some examples and understand how it works, or just look at the algorithm and try to figure it out just by reading it. Usually I like just reading through the algorithm and trying to understand it from the first time. But if I'm not able to do that, I'll either stop solving the problem or just look through the examples. So why did I say that I'm stopping to solve the problem? That's because since I started working on WellCode 1 year ago, I've put all my free time and all my energy into it, and it doesn't make a lot of sense for me to train for programming interviews, because I've had a lot of interviews during my college years, and I passed them almost all. And whenever I'll be back at interviewing with companies, I can just take 2 months and just train really hard and get back to my original level, because this thing is a skill which can be forgotten and you can become worse at solving problems, but it's also a skill which can be learned. So if you're solving problems, you can definitely become a lot better at this thing. Okay, so let's try to make sense about this thing. So if whenever A iterates through the whole array of A, then it means that A is a substring. Substring, I think it doesn't have to be on consecutive positions, so it's fine. If J iterates through whole B, return false. So we iterated through everything and we didn't find anything. If AI equals bj, then we increment them both by 1 and return to step 2. If I equals 1, increment j by 1. J is on b. Yeah, okay. J by 1 and return to step 2. So this thing happens whenever we haven't found anything from A to B. So basically, so after we ran this for a while, I will be equal to the first position of to the first position in A, so it's 1, and B will be the first position in B which has a character which has the first character in A. So this is what happens after the first step, and then if they're both equal, they advance. So we'll be at the second character in A and the next character in B, and then it will still search. No, actually here won't search. So then we set I to be equal to 1, and this is the mistake. Because if we wouldn't have changed, if the algorithm wouldn't contain step 6, this thing would be correct. So it will if also if I wasn't equal to 1. So in order to have a correct algorithm, we just erase step 6 and erase this part if I equals 1. And we'll end up with a correct algorithm for checking if B contains A. Okay, so I think I've understood what the algorithm's about. So let's jump into the drawing board on the text editor, and let's make sense about this problem and solve it. All right, so now we're at the drawing board, and I believe that a test case on which the algorithm works is just having an A, whatever A is, and then have something like let's note this by A, where A can be any character, and then for B, B has to be something like this. His is some characters which don't match with A, and then we have the A string, and then we have some other characters. So if we're on consecutive positions, everything is fine. And we want an example where the algorithm should return true, but it's actually false. And I think by just looking at the example, we may find something. We may find an algorithm. So we have a Bacchus, and now we have to come up with a thing which is not correct. So I think if we have here a bx acus, it would be very easy to make the algorithm fail. And I think so for Facebook it says it's impossible. Why is it impossible? Maybe I didn't understand the problem. Okay, so why is it for Facebook impossible? Maybe I didn't understand the problem correctly, or the algorithm. Should this be a continuous substring or a substring? Because if this is a continuous substring, then it's... Wait, I'll just have to check what substring means. Let's see what JavaScript substring method is. Extracts the characters of the string between two specific... Oh, wait, yeah, this is a continuous substring. And a continuous substring means that all the characters have to be on consecutive positions. And then what I said earlier was wrong, because the algorithm was actually so the algorithm didn't have to work on this kind of test case. So be really careful when you're reading your problems. Don't solve a different problem than the one that you're given to solve. And let's see let's simulate the algorithm on the example provided by them. For me, and now I'm simulating the algorithm because for me it looks pretty much right. So for each step, if they're both equal, they both increment. If I equals 1, we find the first position in B for which matches with the first character in A, and then we try to match everything up. And if it's not, oh, actually, I know how to solve the problem. And if it's not equal, then we set I to 1 and return to step 2. But here's what's the wrong thing. The problem here is that we may find some letters with from A and B which match, and let's say this is, and let's say here there's no match, but we may match and then we will start searching for a match from this position in B. But what if this thing actually matches something, or this thing? I'm trying to construct an easy example in order for you to make sense of what I'm talking about. A, B, A, C, and let's say we have, I'm thinking about it. What kind of example can I give you? Yeah, let's think about this thing. A, B, A, B, A, C, and we have A, B, A, B, A, B, A, C. Okay, so how does this algorithm work? We'll increment both indexes for the first position, for the second one, for the third, for the fourth, and for the fifth one, and here is a no match. And we should have reset the index for B, we should have reset it to here, because as you can see, this string appears here. But we're not resetting anything, we're just continuing with J. So J doesn't get reset anywhere around this algorithm. And now I made sense about what the wrong test case looks like, but now I have to think about a way to come up with a solution. I think this thing uses the prefix function of the Knut-Morris-Pratt algorithm. For those of you who don't know what the prefix function is, it is P of I equals longest prefix of string S from 1 to of S till position I, which is also a substring. It's basically longest of S from 1 till I, which is also a suffix, and it's shorter than I. I remember when I first learned this algorithm, it was really puzzling for me, because I didn't know why the longest prefix, which is also suffix of that string, isn't the string itself. And this is a really useful algorithm used in string matching, and actually not the algorithm. Sorry, the prefix function, which is this array, is really useful whenever you're doing string matching, when you're using Knut-Morris-Pratt algorithm. And let's compute the prefix of this first array. So here is 0, here is 0, here is 1, because A is a prefix and is also a suffix. Here is 2, because AB is also a prefix of this thing. Here is 3, because ABA is also a prefix, and then here is 0. So I hope you understood what the prefix function is about. Here is 0, 0, 1, 2, 3, 4, and 5, I think. 1, 2, 3, 4, 5. Yeah, this is a prefix, is also a suffix, and here is 0 again. And and we need to yeah, and I know how to construct an example. We need to somehow make this thing overlap with itself. So we need to have some sort of um, of overlapping here. We don't need to have to have the string repeated, but we can just find the first place where we have a prefix which is also a suffix and just repeat that string. I think if we would have a backus, this would also be wrong. No, actually it won't be wrong, because if we have a backus, then here it doesn't match, but I is set again to 1. I think actually if we had a backus and a backus, this won't be correct. So it's not enough to search for a non-zero value for the prefix. We also need to find two different values. If if the string consists only of equal letters, then I think that the algorithm works. So for Facebook, it's impossible to find such a test case, because it it doesn't have any position where you have a prefix which is also a suffix. And for FBFBF, why is it impossible here? Let me think. FBFBF 0 0 0 1 2 3. What I'm thinking is we have to have a prefix, like we have to have a non-zero prefix which is also a suffix, and then we need to have a 0. And whenever we're finding the 0, so here if we find the, let's see how it's for a backus. If we find here we have 0 0 1, and here we have another 0, so if we just repeat the same string again, if we repeat the same string again, then it won't match with backus. So what we're looking for a sequence which has a non-zero prefix which ends then with 0. I think that's the case, and we just need to repeat twice that prefix, because what will happen is will match, everything will match until that prefix. So what does this mean? If we repeat this, we have 0 1, we have 0 0 1, and we can repeat this, and here we actually, it doesn't matter, and here we don't have a repetition, anymore. Oh wait, no, I made a mistake, and we need to put a different character afterwards. Sorry, I I lost my thoughts. Let's bring them back in. So you have the prefix, and you want to match the prefix in both of the strings, and then because you have a prefix, you can actually overlap the two strings, because what, okay, I'm doing the explanation again. What we're trying to do is to have a match from B. So we want to match A, some characters in A, and then have something different which doesn't match. And which doesn't match the next character, but it's still something from the beginning of A. And if we look at abacus, I can show you what I mean. So if we have abacus, then afterwards I want to have again abacus. You see, we can overlap this A with itself because this is a prefix which is also a suffix. So basically we're taking the suffix and we're making we are making it a prefix of the previous. We're making it a prefix of A. That's what we're trying to do. So we're actually using the suffix, which was also a prefix, as a suffix. And what 0 tells us is that we won't have any prefix anymore, which is also a suffix. So everything from there on needs to match A exactly. So if we take advantage of this thing and put everything at the end, it will work. So actually what we're trying to do is find the first non-zero sorry, what we're trying to do is find the first prefix, which is also a suffix, and then overlap everything above it. Let's look at the more complicated example. I'm glad they provided it. So for this thing, for this thing we have 0, 0, 0. We have 1, 0, 0, 1. Actually, this one is bad. In order to construct it, what we can do is take the first part, which has the prefix, and then append the last part here. And let's simulate how the algorithm will work. So first of all, I and j will be here, and then after the next step will be here. They match again, will be here. They match again, will be here. And then the next point, they don't match anymore. And when they don't match, this gets reset. I becomes equal to 1, and this thing just advances. And after the first advance, this is wrong because we already missed the only appearance of the we've already missed the appearance of the character. We're not able to find it. All right, so I know how to solve the problem now. B must contain at most 10,000 characters, but actually we need at most double the length of A. Let's copy this thing and save it as problem 3.cpp and solve the last one. p3.text, p3.out, close these things, and yeah, let's go on. So string A, string B. Actually, I don't want strings because it's easier to construct the prefix function when you're not using when you're using one-based strings. So I'll have this B, which will have at most, let's define a constant max length, and let's have char A, which also has max length A. So now we are reading the number of tests, and then we just read the A plus 1, and now we need to build the prefix. And I said build prefix of A and B, and now I'll implement the creation of prefix function, which is build prefix, which takes char A and int p. And now we need to take two indexes. I won't explain how this thing works. You can find lots of good articles on Wikipedia and in algorithm books. In order to understand it, you just need to simulate it on paper. Or maybe at some point in the future we'll release a premium module on WellCode where we'll explain more advanced algorithms. So now I want the length of a. A len is extra len of a, and I need to include C string to use this function. And now I starts from 2 because the position 0 for prefix is always 0, because we need to have a prefix which is different from the whole string. I equals 2. We also have a j which will equal 0, and then I is smaller or equal than length plus plus I, and here we'll do a for loop, and here we'll say while for j is different than 0 and s of j plus 1 is different from, not s, sorry, just being used from programming contests where I'm just naming all the strings s. So while a of j plus 1 is not equal to a of I, then j equals p of j. And if a of j plus 1, forgot to put spaces around operators. So if this thing equals a of I, then I'm able to increase the value of j. So we actually found a prefix, and here I'll say p of I equals j. Okay, let's test this algorithm out. So for I equals 1, int length a equals len of a plus 1, spaces around operators. That's what they tell you at Google or at any other company when you submit code and you forget to add spaces around operators. Okay, I is smaller or equal than length a plus plus I, and t out pi, and then let's put a new line. I'm also printing this out in order to make sure that I did a good prefix function. p3.text. All right, let's check it out. Error, a was not declared in this scope. Max length, sorry, forgot to tell you that it's 2005. I can put just 2001. And what's this complaint about? Okay. N was not declared in this scope. Oh yeah, because I forgot to delete the extra print. Okay, everything is 0. And that means I did something bad. Let's check if I read the string correctly. A plus 1. Probably I did. Yeah, I did read it correctly. So I equals 2. And I is smaller or equal than length. J equals p of j. Okay, so first iteration j won't get in here. It won't also get in here. P of 2 will be 0, and then I becomes 3. This for loop won't be executed, so if a of 1, because j is 0, equals this, then I'll increment j, And here should be 1. Why is it not 1? Let's print. Let's see that I'm passing the right thing here. No, I'm not passing the right thing. Or yeah, here I should have put +1. Yeah, I'm passing the right thing. And what's wrong with this? Oh, length. Length is wrong. I should have put here a+1. That was the mistake. Okay, so if we're looking now, this is 1. I also want to check a more complicated example, AB, C. And let's check it out. So 0, 0, 1, 2, and 0. All right, and now we have to find the first 0 after we found a after we found something which is non-zero. So we have to find the first 0 which has a non-zero value before it. And I'll just modify this for loop. So I'm saying here, if p of I minus 1 is not 0 and p of I equals 0, then we need to repeat the prefix. So we need to print the first I minus 1 characters, if I remember correctly. So what happens? I take the first part, which is non-zero, and then so this was the initial string. So I took the part which was not 0, and then afterwards I've overlapped it, and the match wasn't happening at the position which was 0. So I have to print the characters here. So here I need to, and also I need to break the 4 afterwards. So I need to print 4 and j equals 1. J is smaller than I plus j. See out a of j. And then after I printed this out, this will actually be just the prefix. Yeah, so I actually don't print it until I print it till the value of p of I minus 1. So this is the string, and now I'm at a position where it doesn't match anymore, but I have a non-empty prefix which needs to match. And what do I need to do now? So this is the kind of thing I'm talking about with not practicing. I find it harder for me to just put there the formula to find the indexes. I actually need to think about every step of the way, about every small formula that I need to write in the code. And this thing won't happen if I would be trained. I would just write everything from the beginning. But actually it's better for me because I'm explaining things, and I'm providing clearer explanations, because while doing this I need to explain first of all for myself. So I need to also variable found solution, which is 0. Actually, okay, this thing needs to be here. So if I find this means I found the solution, and found solution equals 1. And if not found solution, then I have to print impossible. And let's see if this is not cout. Let's see if it works on the example input. Oh wait, I already had it. I need to have impossible for case 2 and case 4. P3 case 2 and case before, and I need to create this thing. So now I printed the prefix, which was also a suffix, and then it comes a character which doesn't match. And what I wanted to print was, oh, actually I wanted to print the whole string, I think, or not, no. Yeah, so my mind knows how to do it, but it doesn't know how to write it into code. X, Y, Z, X, and this was the point where I had the match. This was the prefix. So I've written the whole string. Yeah, actually I need to write the whole string or not, no. No, I needed to write everything till the prefix, but then because it was zero, afterwards, because it was zero, I could have just written the whole string and it would have skipped everything else, because on this position is zero, so I'm writing everything to the current position. So I'm writing everything till I here, and afterwards, after I've written the whole string, now I have something which doesn't match, and will reset the index for A. So index for A will be here, but I need to write now everything from the current position till the end, till the end of A. Let's see if it's correct. Now I'm trying to guess a bit what the second iteration needs to look like. So J will be P of I minus 1 plus 1 till J is smaller or equal than length A plus J, and now I print A of G, and let's check if this thing works. So I have a back. No, this is not right. Back. I don't have a backus. Yeah. Yeah, actually, I think I need to print it before I and from then start the prefix. A, B. Yeah, so this was right. So what I'm doing first is printing the prefix 2 times, and because I'm printing the prefix 2 times, this thing is something which repeats itself because we have a non-empty prefix. And because I print the prefix 2 times, at the second time it won't match A anymore. And then I'll just print the string ABA, and here we'll have something which does not match, AB. So when we're here, we already skipped the first letter, so this one goes to the beginning. So this test case is correct. Let's see if the second one is still correct. Actually, I obtained the same thing as while doing it by hand, and let's see for this thing, ABAC. Let's see if I did this correctly or not. I'm testing it, and this thing matches, and this thing doesn't match anymore. And I've already skipped all the characters here in B. And because the way I'm printing, I'm not able to find another string at the end, because the generated string will always be shorter than 2 times the length of A. So in order to do something correct, I just need to be sure that I'm printing something shorter than 2 times the length of A, and yeah, I have to repeat the prefix 2 times. So I have something. So in this part, basically, what I'm doing is printing the string. And because I'm printing the prefix a second time, I'll have the prefix 3 times, but because I'm having a 0 here, it won't match anymore. So here I'm printing the next character after the prefix, which we already are sure that it's not on position I, because if it would have been on position I, then we would have ended with a non-zero prefix on position I. So we are sure that this is correct, and now I can submit the problem. Hopefully my explanation was clear. You'll understand it better if you'd understand the prefix function, the one used by by the algorithm KMP. You can just search on Wikipedia KMP, and I think it will be string matching. I think this is the title. All right, and let's get the input and finish with this contest. Wait, no. Here's download input. Give me the input and start training the timer. And yeah, this is the input, which is long, and let's see how the output looks. I know I'm wrong if there are a lot of impossibles in here. Impossible. Yeah, I have some impossibles, and I think it looks pretty decent. So I can submit out, and the source code. Okay, so I've submitted.
What's up, YouTube? I'm enjoying the evening after a hard day of work. I'm in Los Angeles, California, doing an internship for Google. And the thing I don't enjoy are my results at Facebook Hacker Cup. So I solved the first 2 problems correctly, but for the third problem, I failed the test. It was only 1 line of code which had a mistake, but obviously that made the code incorrect, so I don't have any excuse. But let's use this thing and learn something from it. My mistake was that the prefix function for a string can decrease, but it shouldn't necessarily go to 0. So that was a false assumption which I made during the contest. If I change the comparison of P of I, instead of comparing it with 0, I just need to compare it to P of I minus 1. So P of I needs to be smaller than P of I minus 1. And that condition is enough in order to construct the second string. And while these small mistakes may not be that crucial during an interview, you may get feedback from the interviewer, or he may ask a question which may help you find out that kind of small mistakes. You still need to be very careful. You may catch the interviewer in a bad day and you want to write the code flawlessly. And while these kind of small mistakes may not be that important during an interview, because a lot of times the interviewer wants to help you and he may ask you some questions which may make you find out the small mistakes, you still need to pay attention, and it's better if you write the code correctly from the start. But during contests, this kind of small mistakes may make the difference between a good result and a bad result, and contests matter a lot in your CV. And also when you're writing a real world app and the app is generating revenue, if you have a bug, you may lose a lot of money. So be really careful at the code you're writing. And the practice which I found out to be really good is the following, and I'll provide you with some background about how I developed it. So when I was in high school, I was making a lot of small mistakes, even in contests, and that cost me a lot in terms of results. But after I got got into college and started working on math problems and doing some proofs, some mathematical proofs for them, my brain started developing and started working a lot better, and it helped me even while writing code, because while I was writing code, I was trying to prove in an unconscious way while I was writing code that my code was actually correct. And because I was doing that, I was catching my mistakes while I was writing them, or even before writing something, I was used to think about it, and I was just making a pause for 30 seconds, thinking about what I need to write, and write it perfectly from the first time. So math might help you a lot in finding those kind of mistakes. Another good practice is to be aware that your brain actually wants to trick you, because you're feeling better if you write good code. So your brain wants you to feel better, so it will try to trick you. It will start thinking that what you've written is already correct, that you don't need to test it in order to keep your happiness. But you have to be aware of that, and you have to write tests which make the code fail. Think about what are some cases on which you are unsure that your programs work perfectly, so you need to test your code on those kind of examples. And if you apply those two techniques, your skills will increase a lot, your results will increase, and you will do better at the interviews and at the contest. And if you like this video, don't forget to hit the like button and to subscribe to our channel, because there's a lot more technical content coming up. If you have friends who are also into writing code, don't forget to share this video with them. And until next time, I wish you all the best, and I hope you'll pay more attention at what kind of code you're writing, and I hope you'll catch all your mistakes and you'll write code without any bugs.